won't. And let's see. Oh, we're going. Okay, good deal. Okay, so here's where we were last time. We were talking about divergence, and I've already given you the apology that this comes about very naturally in a context that we're nowhere near yet, right? So this is seemingly coming out of nowhere. The assertions that I'm going to make about how to interpret divergence and very soon this other thing called curl are coming out of nowhere, right? I'm giving you no motivation for them at this moment. I will later, right? So anyway, just as a quick reminder, we define this thing called divergence. This is the notation. This is the formula. And apologies having been made, here's the assertion that I claim of how to interpret it. It represents how much a vector field thought of as a flow of a fluid represents the fluid kind of flowing away from a given region. And we saw this example where you can see it kind of tracks, right? So we have a positive divergence, and as in the interpretation goes, it is to a positive extent that the fluid is flowing kind of generally outward away from where we computed that divergence. Okay, and we talked about some physical interpretations. All right. Here's another example. Now, this one I think also makes pretty good sense. Y'all will notice that this vector field looks like this. Now, that's an exercise. That's something to think through. Persuade yourself that from the algebra alone, you could produce this picture or something, along these lines. Okay, so what's the divergence? Well, you can compute the divergence pretty straight. It's 0, nothing to it. And now let's ask, does that track with our interpretation? And well, if I were to, notice this is at any point A, the divergence is 0. So if I were to consider, let's say this general vicinity right there, is the fluid flowing to any extent sort of generally outward from that region? And well, no, not really, because there is flow outward, but there's just as much flow inward. So altogether in the net, there isn't really any outward flow. So again, this computation of divergence tracks with that interpretation. Okay. All right. Next, premature concept. Curl, and same sort of deal as with divergence. This is a name, this is the notation, this is the formula. Now I will point out that this notation and formula obviously sort of track with the the usual way. So this is a cross product. Cross product is computed as a determinant, symbolic determinant, where you put standard basis vectors across the top. That's how you compute cross products, and this is an air quotes symbolic cross product, of course. And then the first air quotes vector goes in that row, and then the second, this actually is a vector, no air quotes, goes in the second, or in the next position there. So it's the usual cross product symbolic thing with more symbolic nonsense in the form of the del operator being one of the vectors, right? But anyway, if you just compute directly from this formula, you will get the right thing. And just to be clear about what I mean by compute from this formula, in computing this determinant, we'll be multiplying E1, the vector E1, times this determinant right here, which I would say should be and is the y partial of F3 minus the z partial of F2. Right? So now again, that's interpreting as, for lack of better ideas. I guess this is what that ought to mean. That's what I mean when I say, compute according to this formula. And if you just continue in the usual pattern, that will give you the correct formula for curl. Okay. All right. So again, highly premature. I can't give you reasons or context for where this comes from yet. We will do that later. But here's my assertion about what curl represents. And roughly speaking, it tells you how fluid is circulating. To what extent is there what you might call sometimes people call it a vortex, right? It's like a little tornado kind of a thing, right? So to what extent is this vector field representing a fluid that's turning, right? And the thing about a turning fluid is that you can talk about how much it's turning, but you also have to talk about around what axis is it turning, because you can have fluid sort of rotating around a vertical axis like this. You could also have fluid rotating around a horizontal axis like this, or around some angled axis, right? So what axis are we rotating around? So the curl as a vector, and you'll notice, look at this formula, see what it computes. The result's going to be a vector, right? And that vector points in the direction of the axis, and its magnitude tells you how much. Whether there's a lot of rotation of the fluid or just a little bit of rotation. Okay, so again, let's see an example. I've got several examples here. So here's one. Now again, vector field, picture. Make sure you can put those pieces together. Make sure that you can, from the formula there, write down a picture that looks roughly like this, describing what the fluid is doing. You'll notice this is very similar to an example we talked through in detail last time. So it's three-dimensional instead of two-dimensional, but it's very, very similar. Okay, so let's compute the curl. Again, it's plug and chug. The vector field goes there per that representation. The del operator goes there, and cross products as they are symbolic determinants. Like that. So plug and chug, and you just compute that up, and what you get is this vector. Now, what is this telling us? That vector is pointing straight up. Missed. That vector is pointing straight up. That's telling us then that the rotation of this fluid is around this vertical axis. And does that track with the geometry? Well, yeah, it does. Check it out. This vector field, again, we sort of drew pictures of it, and indeed, it is rotating around that axis. Just like curl, just like our asserted interpretation of curl would suggest. Does that make sense? What about the magnitude? The magnitude here is 2. What does that mean about the rotation? Well, we don't really have any way of getting our hands yet on the idea of how much a fluid is rotating, but I just appeal to your intuition. There is such a notion as more and less, right? And so, for example, if I were to put a 2 in front of all of these coordinates right there, all these vectors would be twice as long. That would represent there being sort of twice as much rotation in some sense, right? And sure enough, this would turn into twice as long of a curl vector. So I'll say this, just to keep the units and the precision out of it, the magnitude of the curl is proportional to how much rotation there is. All right, another example. Again, I think this one tracks very nicely. So this vector field, again, easy to persuade yourself it looks like this. Make sure you can do that, right? From the algebra, produce this picture. And you can compute the curl really easily. The curl is 0, and you can also look at the vector field and ask, okay, to what extent is there a rotation happening there? And well, it's not, is it? Right? There's just no rotation happening there. So this again tracks. Okay. All right. Now there is a subtlety that this kind of brings up. This is like I say, just a subtlety, but we're talking about how the fluid rotates or circulates or whatever you want to call it. We don't mean individual particles within the fluid, we mean the fluid as a whole. So this next example gets at that distinction. So let's look at this vector field. Again, make sure you can produce that picture. Make sure you can see the connection from the algebra to the geometry to this picture. You compute this curl. You get a non-zero curl. But wait a minute. Look at the fluid. Particles in this fluid are all going in straight lines. Where's the rotation? Doesn't look like there's any rotation there if you look at it from the point of view of individual particles. All right, but I claim that there actually is a rotation happening here. And the way you're going to see this, the way I encourage seeing this, is don't think about this fluid in terms of particles. Think about something floating in the fluid. So let's imagine that there was some, and let's not worry about gravity and buoyancy. Let's just say perfectly buoyant and something that is just going to do exactly what the fluid tells it to do and ignore other issues. What do you think would happen to that little orange blob if it were in this fluid? Well, I tell you what I think would happen, and that is that on this side it's being pushed in such a way that to suggest a rotation clockwise. But on this other side it's being pushed the other way, but it's on the other side, still encouraging it to rotate clockwise. I think this fluid would make this blob rotate clockwise. I think there is intrinsically kind of a clockwise rotation. It's coming only from the fluid. The fluid is what would make that blob do that. And that is what this curl is detecting, right? The curl being -1. Well, let's see here. I made a bad color choice there, didn't I? The curl, I'll represent that with purple. The curl being this, which points down. By the way, it all follows the right hand sort of geometry. Thumb in the direction of the curl. Look at the fingers of your right hand. Suggests clockwise rotation, and in fact, that's, again, tracks with the geometry here. That makes sense to everybody? So this is a hidden rotation of the fluid. Yeah?
If it's clockwise, how come the note says counterclockwise?
Yes, that's right. So this is a little bit weird. So this gets to something, observation I made before. So if you look at my finger here, right, is my finger rotating clockwise or counterclockwise?
Counterclockwise.
From your point of view, but it looks clockwise from my point of view, right? So there's the same issue here. So, as seen from below, in other words, if I were looking from down here, looking upward, it would look counterclockwise. Yeah, that's right. Okay. All right. Okay, so so you got to be careful about that. By the way, there's a homework exercise. One of the additional homework problems. I'm just going to make a very broad stroke reference to on that homework exercise. It's gonna present a scenario that's not unlike this one, and the details, y'all can read the details of it. But roughly speaking, it's well, wait a second. We seem to have a contradiction. There doesn't appear to be any rotation in the fluid, but the curl is non-zero. What gives? And what you're going to notice in the way the question is phrased is that the suggestion of the phrase, it doesn't really quite come out and say it, but the suggestion of the phrasing is that you can tell the rotation of the fluid by way of the flow lines of particles in the fluid. And that's just wrong. Right? So, roughly speaking, what you're going to find when you'll see this exercise when you get to it. Roughly speaking, the point's going to be the assumption within the question is just wrong, and that's how you resolve the seeming contradiction. Okay, so that's coming up later. Anyway, at some point this semester, it might be chapter 6. Okay. So those are these operators, divergence and curl. Here, this next thing, I just want to plant a thought. I just want to give you a little bit of a preview. This is another sort of lots of foreshadowing. It's going to turn out for reasons that are very sophisticated. that there is a really good motivation to compose these operators as follows. So you all know gradient. We've known gradient for a while. You give me a real valued, scalar valued function and take the gradient, and out comes a vector field. We have recently introduced this idea of curl, where if you give me a vector field, out comes another vector field. And notice the Legos fit together, right? I can take what comes out of gradient, and that is what goes in to curl, so I can compose them, and it fits. Right? And then likewise, there's this thing called divergence, and divergence takes a vector field input. So again, the Legos fit. What comes out of curl is what goes into divergence, and divergence produces a scalar valued function. Okay, so not only do these pieces fit together, but there are some powerful advantages, really powerful advantages, to think of them as naturally being composed this way. And this is, I'm going to talk a lot more about this when we get into chapters 6 and 7. So I'll be able to show you more of the advantages. But I am going to just point out now, because we're here, and it actually is very helpful for certain purposes. Here is one of the really nice interpretations. This is what we call an exact sequence, which roughly means everything has a lifetime of 2. As a for example, let me point out that if you give me some vector field, and if you take the curl of it, and you get another vector field, fine, that's cool, but if you take the divergence of that, you will get 0. And this is what I like to call a lifetime of 2. Right, so born there, survived to here, dies there. 0 is death, right? Does everybody get the metaphor? It's just a metaphor. Don't take it too seriously, right? But I find that's very satisfying. So anyway, lifetime of 2, and this works everywhere in this diagram. So, for example, if you take any non-constant, constants are weird. It messes up the story, so we ignore that case, right? But aside from that, you give me a scalar valued function, and you take the gradient. That vector field, if you compute its curl, will be 0. Again, lifetime of 2. And by the way, there's more examples than that. Here's one. If you have a vector field, and if you take the curl and you get 0, that doesn't look like a lifetime of 2. But it's the second half of a lifetime of 2, because whenever this happens, whenever the curl is 0, that vector field is itself a gradient of some function, and there it is, the lifetime was 2. So you can use these operators to draw conclusions about the other operators in all of these different ways. And by the way, if you write down all the versions of this, there's like 6, or depending on how you think about it. Anyway, there's a bunch of different statements that are all unified into a single statement if you compose, as I claim is really natural, all 6 or however many of those statements there are, they all come into this, they all fit together in this one simple pattern. All lifetimes are 2. So this is what I like to call an eyebrow raiser. That's weird. What are the odds? How come all of these seemingly different theorems they all fit together in this consistent way? It's very unexpected, strongly suggestive that there's more going on underneath that we haven't noticed yet. Anyway, I just wanted to point that out, and there's much more good stuff along these lines that we'll see later in the course. Okay, so lots more cool stuff coming in that direction. And that finishes chapter 3. So moving along, now you're going to notice we're not going to do chapter 4 right now. Chapter 4 comes at the end of the class. This is for kind of strategic, pedagogical reasons. Roughly speaking, and I think I may have already said this, but it bears repeating, the most challenging part of this course is chapters 6 and 7. If it was up to me, I would do chapters 6 and 7 as early as I possibly can. The problem is that chapters 6 and 7 use a lot of stuff from chapter 5 and from chapter 3 and from chapter 2 and from chapter 1. I can't start the course with chapter 6. It wouldn't make any sense. You wouldn't have the slightest idea what I was talking about. You just can't do that, right? But I can push chapter 4 to the very end of the course, because chapter 4 is not necessary for chapter 6 and 7. And that's I'll say the only clean, simple, easy choice that I can make in that direction without some pretty serious trade-offs. And anyway, that's where I'm at in my design of the way I teach this course right now. Is chapter 4 goes to the end, and everything else would go pretty much in order. So anyway, we'll get to chapter 4. We'll just do it later. Okay, chapter 5, we're going to talk about integrals. Chapter 5 is about multivariable integrals. So how's that work? Well, it's a lot like the story with derivatives. We're going to take the idea, like we did with derivatives. We took the single variable derivative. We identified most fundamentally what it was about. And then we came up with kind of different multivariable versions of that and a complicated story. Now, you'll recall also we began with partial derivatives, even though that's not really the best point of view. We start with partial derivatives because it's easy. It's a foot in the door. And then after we developed many more ideas, then we saw that, okay, yeah, look, partial derivatives, it's a nice tool and all. And it's an important tool. We need partial derivatives. They're very convenient for computation. But ultimately, derivatives are more sophisticated objects that we came to realize, right? So the derivative transformation, derivative matrix, different ways to think about it. Okay. All right, so we're going to do the same thing here. I'm going to start with a point of view on integrals that's really not the best. But I'm going to do it because it's easy. It gets one into the win column for us. And it's something we're going to have to do anyway, so we might as well do it first. So again, don't hang your hat on this. I'm about to show you what you should not take as your cornerstone point of view on integration. This is a first attempt, and it has its uses, but don't take this too seriously. Okay, so here we go. Flashback, single variable calculus. Y'all remember this business. Volume of a rotated surface, if you want to compute that volume, right? Then the big idea is you chop it up into little pieces, and each of those little pieces, you say, okay, well, look, that little piece has a cross-sectional area that I can compute. Right, there's that cross-sectional area. And I can multiply that cross-sectional area times this thickness. Missed the... there we go. Area times thickness gives you volume, and then you add up all those little pieces of volume, single variable integral, we're done. Yeah? Anybody remember this? Okay. Let's try the same thing now for a different problem. So here, we again have a volume. We're interested in computing this total volume here. This is no longer a rotated volume. This is now the volume under a surface, specifically the volume under a graph, right? And we're going to, again, very importantly, we're going to start at least looking at graphs, and this graph, that surface, something like that, I can talk about how much volume there is underneath it. Right? Reasonable question? Okay. Well, let's start off the same way we did with the previous problem. Let's talk about breaking it up into little pieces of volume. How would I compute that little piece of volume? Well, okay, there's a sort of a cross-sectional area here. Oh gosh, sort of a cross-sectional area there. And then let's see, there is a thickness which again I would call dy. Right? And I guess I could say that little piece of volume is area times thickness, but the problem is I don't know how to compute this area immediately. Right? If this were a single variable calculus class, we'd have to throw up our hands and say, look, I know what to do if it's a circle. I know what to do if it's a square, and I know what to do if it's a equilateral triangle, right? And different details to worry about. But garden variety, high school geometry, cross-sectional areas is what we have previously been trained to deal with, not wacky shapes like this that are not high school geometry stuff. All right, so this, again, in a high school single variable calculus class, you throw up your hands, you declare defeat, and slink off, right? So here's what we're going to do. We're going to realize that, in fact, that is something we know how to compute the area of, if you interpret it the right way. So what that is, that area that we're interested in here, that is the area under a curve. Where have I heard that phrase before? Area under a curve. We know how to compute area under a curve. Oh, wait a minute. We know how to compute the area under a curve if the curve gives height as a function of horizontal position. In other words, if it's a graph. Well, check it out. This is a graph. Z, height, is indeed the value of our function. Now, you might say, well, that's a multivariable function. I don't know what to do with that. But I would point out it's actually kind of not. Take a closer look here. This curve under which I'm computing the area is defined only for looking at a single value of y. I mean, just look at the picture, right? We have to fix a value of y to even talk about that cross-section. I have to tell you which value of y we're interested in the cross-section of. And once I say that, once I say, okay, we're going to fix a y so that I can look at stuff over here in the picture, well, I've said I'm fixing y. That means y is a constant. And so, in fact, we have z is a function of a single variable x. So I know how to compute that area. It's an integral. Right? It's nothing. It's area under a graph. It's high school calculus. And very easily dealt with then that I can compute this area here as, wrong color, green. I can compute this area as that integral. And area times thickness. Now keep in mind, I'm adding these up as y ranges over various different values. Oh, you know what? I already have. Here, let me do this. We already have this dy set up there. Right. So area times thickness gives you little pieces of volume. These little pieces of volume that we were talking about here. And I can then just add those up as y goes from c to d. So we do an integral. Anyway, let's see here. Let's do it like that. We integrate as y goes from c to d, and boom, we've got ourselves an answer. Right, now this is a weird, I will confess, this is a altogether kind of a weird construction because there's two separate integrals involved here, and let's make sure we're clear on what these two separate integrals are doing. The first integral, depending on what you want to call it, but I start off by talking about going in the y direction. I'm going to slice perpendicular to the y-axis. That gives me this idea of an integral y going from c to d. That integration is adding up little pieces of volume. By contrast, this integral, the inside integral I'm going to call it, that's helping me compute the area of that cross-section as I go across that slice. So they're playing two different roles, importantly different roles here. nevertheless, two separate integrals that I'm using in the same calculation. How we doing? All right. Okay, so that's the big idea. By the way, this is what we call an iterated integral. I say we. This is what is called an iterated integral. I kind of personally, to me, iterated suggests that you're repeating the same process multiple times, and these are not the same process, right? We're doing two different kinds of integrals. Importantly different. So to me, the term iterated integral just doesn't quite work. To me, though, these are very clearly nested integrals, right? Each one's sort of inside the one further to the outside, if you will. So they fit inside of each other, and that's what nested means. So I like to call these nested integrals. You're probably going to hear me call these nested integrals. You probably won't hear anyone else calling them nested integrals. Iterated integrals, the more common term. Okay. Right, so related note, how did I write this down? The very first thing that I wrote down was the dy integral. It's tempting to call that the first integral of the two. It was only second, after I had written down the dy integral, that I wrote down the dx integral. Okay, fine, but now let's think about how would I compute this thing. Can I compute the dy integral first? No, I can't compute the dy integral. I don't even know what its integrand is. The dx integral is the integrand, right? So you can't start with the dy integral. You have to first compute the dx integral, see what that integrand is, and only after you've done that, only after you've evaluated the dx integral first, can you then get along over to computing the dy integral. So there's this backwardsness of a sort. One of the integrals is written first, the other is evaluated first. It's pretty ambiguous if you say the first integral. Does everybody see how this is ambiguous? I mean, that's not clear what you mean when you say first integral. What is clear, no question about it, is you can talk about the inside integral and you can talk about the outside integral. That totally makes sense. So please be careful. You're going to have this strong urge, if you're like every other calculus student I've ever taught, to call one of these the first and one of these the second. You got to resist that urge. Please call them inside and outside. Okay, does that make sense? Okay, also important and it needs to be noted here, you got to keep in mind what roles, which variables are playing at which stage of the calculation. So in particular, if we look at the inside integral here, the inside integral, as previously discussed, that inside integral's job is to compute this area. And for the purposes of computing that area, y is fixed, which means that that variable y is to be treated as a constant. While you're computing that inside integral, you treat y as a constant because it is, literally. Right there, look at it. Y is not allowed to change as you're computing that blue inside integral. So we treat it like a constant because it is a constant. And said differently, notice that the variable that you treat as a constant is the outside variable. So this is a nice simple way to remember this. You don't have to think about the picture every time. When you're looking at the inside integral, the outside variable is to be understood as a constant. Is that cool? Okay. Right. Okay. So what about when you're looking at the outside integral? How should I interpret x when I'm looking at this outside integral? And the answer is there are no x's. If you look at this inside integral, its integrand is a function of y. X is just a dummy variable for the purposes of that inside integral, and when you have successfully finally computed that inside integral, there won't be any x's left. So there is no question of how to treat the x's. They're not going to be there. Does that make sense? Okay. Okay, so let's get our hands dirty. Let's do one. Whoa. So as per the setup that we've discussed, we're looking for the volume under a graph. So we're going to look at this volume right here. You'll notice that I've specified a specific function. This function right here. Now we know what the graph of that function looks like. The graph is, something kind of like that. But we're looking specifically and only at the part that's sitting over this rectangle. And the volume sitting over just that rectangle is what we're trying to compute here. Like so. Is everybody with me? Okay. All right, now before I go on and do this, I want to talk about the notation a little bit. I'm not sure if y'all have seen this notation before. It's very handy. It's a very convenient way to describe a rectangle. The big idea is that the first interval is just telling you what the corresponding interval is on the x-axis. The second interval here is telling you what the corresponding interval is on the y-axis, or whatever is your second variable. And so this weird notation, and that looks like a cross product, and it's not. It's just a different use of the little cross symbol. That refers to then the rectangle whose x shadow is as indicated and whose y shadow is as elsewhere indicated. So handy notation. I'm going to use that a lot, so be on the lookout for that. Okay. All right, so previously discussed, the volume that we're interested in, computed with an iterated integral. We've already made that argument. We don't have to make the argument again. Right? Volume's computed with the iterated integral. So write that down. Notice, real quick before I go on, that the range of values given for x are my x bounds, as they should be. Notice further, the range of values given for y are the y bounds, as they should be. Yeah? Okay. So I'm just following the rules, following the pattern that we've already set up. Now, how do we compute? Well, again, we start with the inside, so we're going to look at this inside integral. How do I compute this inside integral? Don't forget, and this is the really big one, easy to mess this up. Y is the outside variable. That means y is to be understood to be a constant, which, by the way, of course, also means that y squared is a constant. And this is what a lot of students will mess up. What I see happen over and over again. Less and less, the bigger a deal I make out of it, right? But nevertheless, I still do see this a lot. In the same way that students know that that integrates like that, so many students will look at this and want to write down 1/3 y cubed. That doesn't make any sense at all. Y squared is a constant. We're doing an integral with respect to x, and the integral of a constant with respect to x is the constant times x. That makes sense to everybody? It's an easy landmine to step on, yeah.
Can we switch the dx and dy if we switch the...
That's a great question. I'm going to come to that in a couple minutes. Yeah, great question. But, let me put that off for just a moment. Okay, so heads up. Now, again, this is your responsibility, right, as practitioners, soon-to-be practitioners of these ideas. You, as the practitioner, have to pay attention to, wait a minute, which variable's on the inside, and is therefore the variable that I treat as a variable for the inside integral, which variable's on the outside, and thus should be treated as a constant for that inside integral. Okay. All right, here's the second mistake that I see over and over again. Again, the less and less, the more I make a big deal. What do you do with the bounds? Right, x has bounds 0 and 1. A lot of students will write down the 0 and the 1. Will not bother to write x equals. And then they take these values for example, this 1, and they plug it in there, and they plug it in there, and then they forgot what they were doing. It just says 1. That says plug in the 1 for like the variable or whatever, and then they plug it in for y also. And of course that's wrong. So let me do that in red as the warning, right? We don't plug it in for y. That's not a y value. Y is y. Y is a constant. It's whatever value it is between 1 and 2. You don't plug in x's values for y, right? Easy mistake to make. The hack that I use myself, I encourage everyone to do this, is to when you recopy those values, in recognition that x is the variable that you are plugging that in for, go ahead and write down x equals specifically. That'll be your little visual reminder. And even if you understand the danger, it's still possible to oops it, and this will help reduce oopses. And I think there's a lot of value in that. It's worth the second and a half it'll take you to write x equals 2 different times. Well worth the second and a half. All right. Okay, so you plug in these values of x, you get this. This then is your integrand for your outside integral. Notice, as promised, no x's. The x's are all gone. Well, they should be all gone, right? This is just telling me my cross-sectional area as it depends on y. X was a dummy variable for the purpose of computing that cross-sectional area. It has served its role. It doesn't. Not only does it not need to be there anymore, it should not be there anymore. Okay. And then single variable calculus, y'all know how to do that outside integral is literally straight up single variable calculus. Okay, how are we doing on this example? Okay. All right. Let's see here. Yeah, good. Okay. Okay, so somebody was asking about can you switch the order of the integration, and I'm going to leave this as an exercise for y'all to work out. This is a nice exercise. We've already discussed this one, that you can compute the volume by doing the dy integral on the outside and the dx integral on the inside. Now, I'm going to ask y'all to entertain doing it in the other order. Namely, what would happen if you tried to do your x slicing on the outside What if, in other words, in this scenario right here, instead of going in the y direction and looking at slices perpendicular to the y-axis, what if you went in the x direction and were taking slices perpendicular to the x-axis? You'd get a different picture. You'd have a different cross-sectional area. That cross-sectional area would be a function of different variable. You're going to what it's going to turn out to be is you're going to go through an argument that's morally equivalent to this, but with different pictures in different directions, different variables playing different roles, a lot of changes, but morally kind of the same, right? And I think it's a fantastic exercise to fill in those blanks for yourself. So redraw these pictures correspondingly, redo this argument adapted correspondingly, and what you're going to find is that indeed it works out fine, and you can totally do this move right here, right? So you can take what was the outside differential and the outside bounds and the inside differential and the inside bounds, and you can just do like this. Inside to outside, outside to inside, and that's fine. Everybody see what I want you to do? You're going to get the same answer either way, because, of course, you're computing the same volume either way. All right, now, I do have to give you a quick warning. It works out so nicely because our domain is a rectangle. Now, that's all we're even talking about at this point, right? Notice in the question that we were entertaining here, we were only considering what happens if we're looking at the amount of volume sitting over a rectangle. So when I say this only works for a rectangle, well, that's all we're talking about. So that doesn't seem like an impactful statement. We are very soon going to be looking at an analogous question of what if we were interested in the volume over some other sort of a shape that isn't a rectangle, and that does change things in some different ways, and we'll figure out how to deal with that, right? That's coming up soon. The point I'm trying to make here is that when we adapt to non-rectangular domains, then this doesn't work anymore. You can't just do that and this for non-rectangular domains. If it's not a rectangle, then you cannot just do the switcheroo. So we'll see how that plays out later on. Okay. Now here's a subtlety. So I want to first let's do a quick flashback. Let's see. Well, here. Let me start with this. Here's a flashback. Y'all remember in single variable calculus, the very first thing you did is you computed in single variable the area under a graph. And then same exact construction allowed you to compute all sorts of other things, like the amount of mass. If you have mass distributed across an interval, typically they talk about like a metal rod or something with a non-constant density, and it's more mass per unit length over here and less mass per unit length over there, and how would you add up all those little pieces of mass along an interval? And the exact same construction, an integral, does that too. And it's lovely how the same construction answers a bunch of different questions. Okay, well, are we so fortunate here? What if, we know how to compute the volume under a graph surface. What if I wanted to compute the amount of mass sitting over a rectangle instead of the amount of volume sitting over a rectangle? Seems like an analogous question. Tempting to just write down the analogous answer, you would think. Good news, bad news. The good news is that this will get you to the correct answer. The bad news is the argument doesn't make any sense at all. And I want to try to persuade you that this argument doesn't make any sense, because I think it's important to realize why we need a better argument, right? So I'm going to show you all a new construction that is not an iterated integral in just a couple of seconds here. And I need to persuade you that we need it. So you'll understand why we're going to the trouble of creating it. Okay. All right, so here again is our iterated integral. Let's kind of talk through what we did with this. The whole point of the integrand is that it tells us height, and then the whole point of the dx here is that tells you a little piece of length. Let me go back to the picture to make this clear. Looking at this right here, right? We had height was the integrand, and then dx's job was to tell you that little sort of width, and height times width gives you area. And that whole area is the sum of the little slices of area, and that's how we computed that cross-sectional area. Okay. Cool. So as noted here, this is how you compute area, and area has this feature that the whole is the sum of the parts. And by the way, how do I know that? How do I know area has this feature that the whole is the sum of the parts? Because I have this very intuitive geometric understanding of what area looks like and how it behaves, because we've been looking at pictures of area for years and years and years now, and this is, dare I say, obvious that of course the whole area is the sum of the pieces of area. What could be more clear? Okay, now, does this same thing work? If I'm considering now mass, and I'm given that the mass is distributed across an area, so I can talk about mass per unit area, can I make this same sort of an argument? And let's give it a shot. Well, This being mass per unit area, notice in this inside integral, the very first thing that I have to do to it is multiply by a length. And now I ask the analogous question, is this something that I can identify? And if so, is it something that I have extensive, natural, intuitive understanding of, and does it behave in this special way where the whole is the sum of the parts, just like area did? No, it isn't. It's a mismatch. Mass per unit area, the idea of mass per unit area is that if you give me an area, I can multiply mass per unit area times area and get mass. The idea of mass per unit area is that you multiply it by areas. That's what its job is. That's what it's intended for. If you multiply it by something that's not area, I don't know what you get. That's not a thing. And now you can make arguments. I know, very clever little arguments. You can say, okay, well, area is length times width, and so the lengths cancel. Maybe we should interpret this as mass per unit width. What's that? The mass is not distributed across widths. What do you mean it's mass per unit width? And by the way, does mass per unit width have this accumulation feature? Is the whole the sum of the parts? I don't know. I don't even know what that thing is. Right? Everybody see the problem? Right? So this is a nasty little problem here. And roughly speaking, in this one scenario, when you're computing volume, specifically and only volume, then this idea that I have to make sense out of is something that I have a previously existing intuitive understanding of, and that was lucky. And it is a peculiarity. It only makes sense in this way for volume. And for any other kind of question, whatever this other application might be, no such luck, and we're dead in the water. And we cannot continue this argument. It doesn't go anywhere. Everybody see the nasty problem? Okay. All right. Okay, so how do we deal with this? How are we gonna compute? I mean, let's face it. In the real world, we need to compute stuff. Very rarely are we computing just the answer to geometry problems. Most of the time in the real world, I'm computing physical things. Y'all are engineers, largely, right? Y'all are going to be computing mass and work and voltage and stuff, physical things. This tool does not work for them. Okay, so there is a solution to this problem. Now, real quick, I want to flash back and talk about single variable integrals. So I hope that everybody is good to go on Riemann sums and the definition of an integral. If you're not, this is a time to brush up on that. Make sure you're good to go on this. Now, for whatever it's worth, if you have, like, if you know kind of the mechanics, like if you recognize that formula and this formula, but you've never really quite understood what the purpose of this exercise was, and it seems like an awfully tedious way to compute something that's much more easily done with the fundamental theorem of calculus, and why are we doing this, right? If you find yourself thinking along those lines, I have a video that I've put together that discusses why we care about this construction, why we care about Riemann sums, why they're important, and I'm going to give you a very rough discussion of that here. If you want to hear the whole story, then go to my YouTube channel, and it's a miscellaneous topics playlist. And I believe the recording is called "What is an Integral?" It's about 30 minutes, and I address a lot of what I'm about to say here, and much more. So so here's a sort of a logistical representation of a bunch of different ideas in calculus. What most students see in high school calculus is they start with the question of area under a curve, they define that to be an integral, and then they compute with the fundamental theorem of calculus to get an answer. And then they say, suppose you wanted to answer some application problem, like you want to compute mass. Well, It's a one-dimensional mass. Let's draw the picture just to be emphatic about this. We're talking about on an interval on the x-axis, computing the amount of mass sitting inside of that interval. Notice the picture is one-dimensional, and then they just come out and just shamelessly say, yeah, we're going to compute that because it's area. And I'm like, for one thing, what area? I don't see any area. For another thing, yes, I understand that you can talk about the graph of the density function, and the graph does have an area, but what's that got to do with mass? I think there's a pretty big hole there, right? That's huge. Now, this can be done. You can make that connection, but let me show you how that connection gets made. The connection gets made by taking the mass in question, rewriting it as a Riemann sum, and then subsequently saying, hey, by the way, there's an area, namely area under the graph, and we could rewrite that as a Riemann sum. So mass and area are both equal to the same Riemann sums, and therefore I can claim that mass is area. And yeah, that's a valid, sure, that's true, but now I have the following rhetorical counter, which is once we've made the connection that mass is computed with a Riemann sum, well, we already know that Riemann sums are what integrals are, and we can compute with the fundamental theorem of calculus. Why are we talking about areas? We don't need area for this, right? Okay. So last point I want to make concerning this picture and this story is a reasonable question. You know, what do I have against the idea of area? Right? I know I seem very opposed to interpreting integrals as areas, and I'm not really. It is a reasonable interpretation, but it is unnecessary. And what we're going to find is that when we start writing down the analogous picture for multivariable integrals, this is going to be a problem. It's not a problem in single variable calculus. It's a nice little geometric picture. It's a nice visualization tool. Sure. Cool. For single variable calculus. And when we get into some higher dimensional stuff, it's impossible to make sense out of. So relying on area as a crutch for understanding what really should be taking a question, turning it into a Riemann sum, aka integral, and computing what should be entirely nice little argument, just like I have there in purple, introducing an unnecessary what is eventually going to be a problem. It's just a bad idea. Okay, so heads up on that, and let's move along, I suppose. Oh, yeah, so last thing I wanted to say on this, concerning all this business. Whether you want to think of mass as being an area, that's up to you. That's fine. I suppose. I don't encourage it, but I suppose you can. We certainly don't need it. But more to the point, this is not an immediate arrow that you can draw. You can't make this connection without Riemann sums, because you have to first connect mass to Riemann sums and then subsequently connect area to Riemann sums and observe that they're the same Riemann sum. So as a direct argument, you can't do that. And it's important that you don't on tests and that kind of thing. And I have a double integral version of this diagram that we'll talk about in a couple minutes. But for the moment, let me just point out, that argument does not hold water. Okay. All right. Okay. So here we go. How would I generalize this idea of a Riemann sum? I emphasize Riemann sum being the definition of an integral, and we want to generalize integrals. I need to generalize the idea of a Riemann sum. How might that go? And so, roughly speaking, broad strokes first. Very often, in a single variable calculus situation, you have some quantity that's distributed over an interval. You want to chop that up into little pieces. Consider the pieces one at a time, and then add up all the pieces. And this is what I like to call the chop it up, add it up argument. You take your interval, you chop it into little pieces. On each little piece, the question is easy. Mass per unit length times length, stuff like that. Then you add up all those pieces. Okay, so that's what we're going to be mimicking. So we're going to take this question of, okay, how much mass is distributed over this area? Right? How would I add up all those little pieces of mass for all these? Well, I'm going to chop this up into little pieces. So slice it up like that. But then I also, of course, have to slice it up in the other direction too. And now, check it out, I've got a bunch of little pieces, and I can argue that on each little piece, like let's take this little piece right there. If I want to know how much mass is in that little piece of area, there's no problem. I know what the mass per unit area is. That's given for the question. If I know mass per unit area, that's an area. I can multiply mass per unit area times area, and that'll tell me mass. No funny business. None of this problem right here of trying to multiply mass per unit area times length. This is the disconnect. That's a swing and a miss. Dead in the water. I don't even know what that is. Right? No problem here. Here I'm literally multiplying mass per unit area times area as it was intended. Okay. And then I have to add up over all these pieces. Now, admittedly, that's how do I say I'm going to add up over all those pieces? Well, I'm just going to write it down for the moment. And by the way, I know I totally get that what y'all are probably waiting for me to get to is where's the part where I can actually compute this, right? Yeah, I got it. No problem. We'll get there. That's fine. Nothing to worry about. But strategically speaking, big picture, the whole point here is that, each little piece of area, you could multiply mass per unit area times area, or perhaps, like if this was the state of Wyoming or Colorado, take your pick, population per unit area times area. Add up over all these little, counties or whatever, right? But the point is, the pieces fit together, and the whole sum of the parts, chop it up, add it up, it all makes sense. It fits, it works, it's fine, right? Okay. All right, so that's the big picture strategy. Now there are some details to look at. You're going to notice, if I can get that, there we go. You're going to notice that as you chop up the area, you are also, in effect, chopping up the x-axis. And y'all will recognize these old formulas for how you note the various chop points as you chop up the x-axis. And I'm just going to observe, likewise, as you do these horizontal slices, you are chopping up the corresponding piece of the y-axis. So you're going to have y0, y1, y2, etc., and you get analogous formulas there. It's the same basic idea. You got the interval from C to D. You chop it up into n pieces. That gives you delta y is d minus c over n. It's the same idea as where the delta x came from. Just it's on the y-axis instead of the x-axis. So all those that's just detailed devils, right? And you got to look at them and you got to think it through, and right? But it's just details. Okay. All right. So altogether, then, this is how we're going to compute the amount of mass in this region, or the amount of population in this region, or the amount of work it would take to polish the floor that's spread out over this region, right? Whatever you can say the whole is the sum of the parts. this is how we're going to compute the whole, by chopping up the little parts. Is that cool? Okay. All right, so this is a different kind of a Riemann sum. So this is going to make our definition of what we call a double integral. A double integral is defined by this expression right there. And so really all I have to do is tell you the notation. Well, of course, I've got to tell you what the integrand is. So we'll, whatever the integrand, whatever the thing is that gives us the stuff per unit area, that's going to be the function we'll just put in the middle. That's what we call the integrand. Then I need to tell you what the rectangle is. The rectangle here is going to have various A, B, C, D, and that's got to be indicated in the notation as well. And then you'll notice that on each little piece, like if I want to talk about what is the area in that little piece, what I have in purple there, well, the area is going to be, well, it's height times width. That's the delta x, delta y. Nice little shorthand notation. We call that dA because it represents literally a little piece of area. Right. So the notation's kind of, sort of reasonable, I think. And this is our definition. If I can get this to cooperate. There we go. This is our definition of a double integral. Denoted like this by that formula. Is that cool? One important thing, so going forward, whenever you see this notation, and you're going to see it a lot, right? This is a very, very common object. One of the big, this is on the Mount Rushmore of objects that we're going to discuss certainly in this chapter, probably the course. I think it's really important to always remember that this is just a shorthand notation. Right? Don't think of this as being, this is where you compute certain antiderivatives or something. By the way, we still don't know how to compute this thing. Right? So we'll get to that in a minute. But make sure to remember, this is just a shorthand notation for a Riemann sum. That's what an integral really is, very importantly. Single variable calculus or multivariable calculus. An integral is a Riemann sum. Okay. All right. A couple of quickie absolutions. The book gets a little fussier with the definition. There are good reasons for this. It's not unnecessary complication. This business about using irregular partitions and arbitrary test points is very important for making this a meaningful, non-arbitrary definition, and there's some lovely math that I would love to talk about. Right? That would make me happy to spend a bunch of time talking about why all this stuff here is important, but it's not what the course is about, and so despite my preferences, we will not be talking about irregular partitions and test points. So when you see that stuff in the book, you can ignore it. For our purposes, we will only be considering integrands that are continuous, and for continuous functions, for continuous integrands, all this business is completely unnecessary and doesn't accomplish really anything to speak of. So anyway, not your problem. Okay. All right. So let's see a quick example. Now, arguably, we've already kind of done this example. We've already talked about if you have a rectangle over which you look at a graph. Over which you look at a graph, right, of some function, and if you want to compute the volume sitting under that graph over that rectangle, you compute that volume with an iterated integral. We've already done it. We already have an answer, right? Old news from earlier in the lecture. So why am I doing this again? You'll see why in just a moment. But let's just observe real quick that this totally fits in our situation, because I can take this rectangle and I can chop it up into little pieces, look at the volume over individual little pieces, right? The amount of volume sitting over just that little piece of the rectangle, I can easily compute because there's a height, which is z, which is therefore the value of the function. And there's an area of the base, little piece of area there, that is delta x, delta y. Yeah, whole is the sum of the parts. Right? I like to think of these as a bunch of little French fries, and the total volume of your biggie French fries is the sum of the volumes of the individual French fries, and so this adds up. Let's see here, adding up over the entire rectangle. Turns this exactly into a Riemann sum. It's exactly the definition of a double integral, and so all together the total volume is that double integral, which we still don't know how to compute. Is that cool? All right. Okay, real quick, summarizing where we're at. I've shown you a bunch of stuff about volumes and graphs and integrals and applications and stuff like that. And so here's kind of where we're at. Just a quick reminder: the very first thing that I did is I took the volume question, we rewrote it as an iterated integral, and then we computed with the fundamental theorem of calculus. That was our first step. Again, it has its purposes. I made the observation right after that you can't take stuff like mass and immediately argue it to be an iterated integral because it doesn't work out. You're multiplying mass per unit area times length. It's a disconnect. It's a swing and a miss. I don't know what that is. That argument doesn't hold water. So you cannot do that. Okay. But then we defined this thing called a double integral, and as we just observed, you can compute volume with a double integral. That was our last example there. And I also constructed double integrals in the first place so that all kinds of different applications could be computed with double integrals. And again, you can compute population, because population per unit area times area gives you population. The pieces fit. It's no problem. Likewise for tons of other stuff, and we'll see lots of other applications. So this is kind of where we're at. And I should point out further, we've also observed that you cannot immediately just claim mass, two-dimensional mass, to be a volume. It doesn't make any sense. Likewise, if I wanted to compute the population of Colorado, and I just go around claiming that the population of Colorado is a volume, what are you talking about? That doesn't make any sense. The population is distributed over an area, not a volume. What volume are you talking about? It's not a thing. So another you can't do thing. Okay, so this is where we're at, and it's a powerful little moment here, and I'm going to notice that we have then computed volume in two different ways, and this proves this very useful result that anytime you have a double integral, you can rewrite that double integral as an iterated integral. And now you may even already kind of see we've connected the dots. We have a path towards solving problems now. And again, this is not mathematician formality, sort of rigor, abstraction kind of math fun, right? This is very practically speaking. If I want to compute the amount of mass or the amount of whatever physical thing, we have a three-step process. First, write it as a double integral. Second, observe that double integrals are iterated integrals. Third, plug and chug with the fundamental theorem, and that will do it. Right? You can solve many, many, many different applications by this three-step process. And I emphasize that all three steps are important. You have to have a double integral there. Otherwise, it looks like you're doing this. It looks like you're just arguing that that iterated integrals immediately address application problems, and they don't. The pieces don't fit, right? So that you got to have the double integral to make it clear that that's not what you're doing. And then you also have to write down the iterated integral, because that's all we know how to compute, right? We don't have any sort of way to just directly, in general anyway, compute double integrals without iterated integrals. So you got to have both of these intermediate steps, and that means that it is unavoidably a 3-step process. And this is where we'll pick up next time. Y'all have a good one. Is today Friday? Yeah, right. Oh, yeah, I forgot we were talking about that. So happy weekend. See y'all on Monday. Yeah, have a good one.